We have the June 2013 Regents exam. Question 1. Which term identifies a scalar quantity? All right, let's know our vectors. Most things are scalars. A scalar, of course, is something that just has magnitude. It just has an amount. And a vector has a magnitude and a direction. More often than not, things are scalars. Let's list our vectors. Let's see, what do we have? It looks like these are vectors. Displacement, velocity, acceleration, force, impulse, momentum, electric field, and magnetic field. These are quantities that have both magnitude and direction, and more importantly, they obey the laws of vector addition. So the other things are scalars. So let's take a look at this problem. Displacement is a vector, momentum is a vector, velocity is a vector, and time is a scalar. Time is a scalar. So the answer was time. Time has no direction. I know sometimes we say time goes forward, but that's just more of a euphemism. It's not actually going forward. It's progressing, I guess. I don't know. Anyways, let's erase that. Know your vectors. Know your vectors. One thing that is not a vector, which some people it's not unusual to mistake as a vector, would be current. Current is a scalar. Current is a scalar. Certainly when charge is moving, it has direction, but current is defined as, it's a counting. It's the amount of charge that passes in a given amount of time. And more importantly, it doesn't obey the laws of vector addition. If you had a circuit like this, and you had 2 amps going that way and 2 amps going this way, we would have the same amount of current everywhere because this is just a series circuit. Those don't add up to 0. If those were vectors, then maybe they would add up to 0 because if you added those 4 vectors. So current is just, it's really accounting the amount of charge that goes by in a given amount of time. Question number 2. 2 20-Newton forces act concurrently on an object. Oh, let's draw this. Make sure we draw. Let's warm up our hand. Draw, draw, draw in this. Here's my object, and I'm going to have 2 20-Newton forces acting concurrently on it, which will produce a resultant with the greatest magnitude. So they're asking for some sort of extreme event. Extremely large in this point. Extreme physics! Extremely large. And so we have 2 20-Newton forces. So if we want to go extreme with this, we could take a look like that, and they're in the opposite directions. That seems to be extreme. And another extreme thing might be to have them act concurrently, and concurrently means that they're acting at the same time, right? And so we have 20 newtons here, and in the same direction, 20 newtons there. That seems extreme, and then we could have anything in between that. Well, what's the angle between them? Well, this is 0 degrees. The angle between them is 0 degrees, and here the angle between them is 180 degrees. So which one is going to give the greatest resultant force? I would say this way. When these are going to add up to like this, I could redraw this. I could add those up. We have a 20 Newton, and I could add that to a 20 Newton using the tip-to-tail method. And those add up to a resultant that looks like this. Okay, so they have a resultant of 40 newtons. This would have a resultant, this one would have a resultant. If I added these up, I would go 20 newtons, and then I would add it, let's draw that, 20 newtons, like that. And the resultant would be 0 newtons. This resultant, which would be a force, of course. So let's actually label the resultant as a force. The force is going to be 40 newtons. And that would be the magnitude. And in this case, the direction would be that way, to the right. All right, that was number 2. So I guess the answer was 1, 0 degrees. Make sure you draw a picture. It makes these problems easier. All right. Number 3, a car traveling west in a straight line on a highway decreases its speed from 20 meters per second to 23 meters per second in 2 seconds. The car's average acceleration is what? All right, let's draw a picture. Here's my car, like that. And I'm going to say that east is that way. And I'm going to say that's plus. So I'm going to say west is that way, and I'm going to say that's negative. All right. Cars traveling west. So at the beginning of the problem, it's V initial is that way. And it decreases its speed. So let's write it down. It's V initial equals negative 30 meters per second. And it decreases its speed. So a little later, it'll be farther down this way. A little later, over there later, it's going to be going like this. And V final, it's still going to be negative 23 meters per second. And it's going to take 2 seconds. 2 seconds. And I should give myself 3 significant figures on all of those. The car's average acceleration. Well, that's all we do in this class is average acceleration. So it just says acceleration. It's technically the average acceleration. Is the change in velocity divided by change in time. Of course, acceleration is a vector. So a change in velocity is going to be V final minus V initial divided by time. But negative is just a placeholder. That's because our calculator doesn't understand right and left and stuff like that. The answer will be 3.50 meters per second squared west, because west is negative. Look at that. I'm going to box my answer, even though it's multiple choice. Make sure on the part 2 that you are boxing your answers. The answer is 2. 2. The answer to 3 was 2. This is kind of a plug and chuggy problem. In a race, a runner traveled 12 meters. Okay, so they didn't give us any direction, so I guess that's 12 meters is going to be the distance she travels, and it's going to take her 4 seconds. Looks like we have 2 significant figures in both of these. As she accelerates uniformly from rest, V initial is 0. All right, so she starts in rest. What's the magnitude of her acceleration? All right, they just want the magnitude. Acceleration, of course, is a vector, but they just want the magnitude. Oh, this is Plug and Chug City. Some of you are so comfortable at this point. You may be sleeping. Let's see. We're going to use El Grande, I think. Let's see. D equals VIT plus 1/2 AT squared. V initial is 0. How convenient. D equals 1/2 AT squared. And let's see. Acceleration is going to equal 2D over our time squared. And that looks like it's 1.5 meters per second squared. Again, they didn't ask for direction, so it's just a magnitude thing. They actually said the magnitude. So I guess the choice was 2. 2. A projectile is launched at an angle above the ground. The horizontal component of the projectile's velocity Vx is initially 40 meters per second. The vertical components of the projectile's velocity Vy is initially 30 meters per second. What is the component of the projectile's velocity after 2 seconds of flight? Neglect friction. All right, so let's put this thing on the ground. It doesn't matter because it's not going to land during the problem. So we have this projectile. I'm going to make it a lacrosse ball. It's a lacrosse ball. And let's see. It has a horizontal component of 40 meters per second. So it's going to be going that way at 40 meters per second. That's Vx initial. And in the y direction, looks like we're going to be 30. So a little smaller. 30 meters per second. Vy initial is 30 meters per second. These are all set up. There's vector addition here. These are all set up for, let's keep in mind what it is. This is all set up for the parallelogram method. Right? We could add those up, and this would be our total velocity. So the ball was going like that. And of course, it's going to go parabolically, sort of like that. All right. What are its components 2 seconds later? Okay, so we have an x and y problem. Let's break this into its components. Let's see, we have x and y. Let's make a t-chart so we don't have to carry a bunch of subscripts around. And okay, so let's take a look. Well, the velocity in the x direction is going to be constant. Constant velocity because there are no forces in the x direction. Since there are no forces in the x direction, it's a constant velocity. No unbalanced forces. Well, if there are no forces, there are no unbalanced forces. So it's a constant velocity. So that's going to stay at 40 meters per second. So our answer is going to be either 1 or 2, right? Right? 1 or 2. And V initial in the y will change, of course. Positive 30 meters per second. I'm going to say up is positive and down is negative, and then I'm going to call acceleration negative 9.81 meters per second squared because I said this way was positive. All right, that's an A. It doesn't look like an A. Now it looks more like an A, but an ugly one. And 2 seconds. 2 seconds is the time. So let's see. In 2 seconds, it's going to be going 10 meters per second up, right? It's going 30 meters per second. After 1 second, it's going to lose 10 meters per second because it accelerates down at 10 meters per second. So in 2 seconds, it's going to be going about 10 meters per second. They want to know what is V final. Well, I can see right away. That's going to be going up at 10 meters per second. The answer is 1. Because after 1 second, it slows down to 10 meters per second every second. So after 1 second, it's going 20 meters per second. After 2 seconds, it could be going 10 meters per second. But those of you who are very uncomfortable with that, let's solve this using plug and chugness. All right, plug and chugness. All right, so I guess we'll use V final equals V initial plus AT, or delta T, or whatever. 30 meters per second plus a negative 9.81 meters per second squared times 2 seconds. 10.4 meters per second. But if you take a look at your problem, we only had 2 meters. Let's see, this should have a decimal point there. We had 2 significant figures here. We had 2 and 2. So the answer was 10 for the y component and 40 for the x component. So the choice, of course, was 1, which I did a while ago. You're saying, why are you still talking about that, Mr. Belling? I have things to do. I have can jam that I need to play. Mr. Belling's wasting my time again. A ball is thrown. Uh-oh. No, not thrown up. A ball is thrown with an initial speed of 10 meters per second. At what angle above the horizontal should the ball be thrown to reach its greatest height? Well, let's see what our choices are. 0 degrees. So if I'm standing here, throw a ball 0 degrees relative to the horizontal, that'll be that way. It's not going to stay in the air very long. It's going to hit the ground right away because I didn't give it any upness. So I'm really looking, if I want this ball to be in the air a long time, I want to give it maximum upness because they are giving, this is 10 meters per second. Either way we do it, it gives 10 meters per second. I could go at 30 degrees at 10 meters per second or 45, and that might be like that. But really, straight up in the air, 10 meters, that way, if I go 10 meters per second, if I want this to be in the air as long as possible, I'm going to throw it as hard as my arm will let me, I'm going to go straight up. Okay, that's going to go highest. I went straight out, it would go to least, right? And then everything in between would be in between that. So the answer was 90 degrees. If I throw it straight up in the air, the angle with the horizontal, relative to the horizontal, would be 90 degrees. So that would be choice 4. 4 is the answer to 6. Which object has the greatest inertia? A 0.01 kilogram a 30 kilogram a 490 kilogram or a 1500 kilogram I am going with the 1500 kilogram which is 4. Okay? The amount of inertia that something has is strictly a matter of how much mass it has. Remember, inertia is the reason that things stay at rest or keep moving if they're already moving. An object in motion wants to stay in motion in the direction it's going and all that if there are no unbalanced forces on it. That's because of its inertia. It's a basic property, and it's strictly due to the object's mass. So I guess 1500 kilograms seems like the most mass to me. Well, let me check. Yes, 1500 is the largest number. Kilograms, so 7 was 4. A 8 Newton wooden block, okay, it weighs 8 newtons. It's being pulled down with 8 newtons of force. Remember, that's what weight is, right? Pulled across the floor at constant velocity. What is the magnitude of the force of kinetic friction between the block and the floor? So the force of gravity on this thing is 8 newtons. That's the force of gravity, that's the weight. It's being pulled at constant velocity. Constant velocity. What do we know when we see those magical words that make me all tingly because I learned so much? Constant velocity. What do we know about the forces? We know that they must be balanced, okay? It must be in equilibrium. If it's a constant velocity, so the forces are balanced. If there's a force this way, there must be a force this way. Let's see. Let's say that the velocity is this way, just for the sake of argument. There's our velocity vector. The velocity is that way. This is a force vector, of course. What is the magnitude of the force of kinetic friction? All right, if it's going that way, friction is opposing the motion, so let's say it has a force of kinetic friction this way. There must be something pulling it in this case, because it's a constant velocity. There must be a force this way. They don't say what it is, but it doesn't matter. What is so there must be a force this way. Don't know what it is. You know, we don't know what's pulling it. Might be rope, I don't know. I don't know what it is, doesn't say. What is the magnitude of the force of kinetic friction? All right, now they said it was, there must be, of course, a normal force equal to the gravitational force because it's in equilibrium. All my vectors are crossing. That is so disappointing. Velocity, let's just say it's that way. All right, well, they gave us a lot of information. They said a wooden block on a wooden floor. So we have that. We have the coefficient of friction of a wooden block on a wooden floor on the front of my reference table right there. 0.30 is the coefficient of friction. No units because it's a ratio of two forces. So the force of friction is what the two surfaces are made out of and how much they're being squeezed together, which is the normal force. So that would be 0.30, which is wood on wood, times the normal force, which must be 8 newtons. These must be balanced, otherwise it'd be accelerating up or down if they weren't. And there's no reason to believe that it is. What choice is that? That is 1. Choice 1. All right, there we go. Which situation represents a person in equilibrium? I should erase first. Something's equal. So what's equal? Well, the forces are equal. Now, what does that mean? Well, it means the vector sum of the forces, right? It means the vector sum of the forces. That if I took all my forces that one, and add it to that one, and then there must be that one that way, and that one that way, and they must add up to 0. They must equal, or more simply, in our Regents courses usually, if we have 4 newtons that way, we must have 4 newtons that way, and if there are 3 newtons that way, there must be 3 newtons that way. All right, it's in equilibrium. The forces are equal. Okay, what else do we know about equilibrium? Well, in equilibrium, it's important to understand the motion of an object in equilibrium. It's either at rest or constant velocity. If it was already at rest, it'll stay at rest. If it was already moving, it would stay moving just like it was. All right, a child gaining speed, nope. She's not at rest or constant velocity. She must be accelerating. A woman accelerate, no, she's accelerating. A man standing still, I'm liking this so far. Let's see if there's anything else that we would find objectionable. On a bathroom scale, I'm fully okay with that. A teenager driving around a corner in his car. Couldn't he be driving at constant speed? Wouldn't that also be equilibrium because he's constant speed? No, it would not, because constant speed is not constant velocity. Notice, they threw a little fly in the ointment. They said he was going around a turn, like that. So he must be accelerating. He has a change in velocity, because even if he was going 30 meters per second, at this point, if he's still going 30 meters per second, he does not have the same velocity. He has the same speed, but he's going a different direction, so he has a different velocity. So the answer is a man standing still on a bathroom scale. All right? If he had been doing jumping jacks or squat thrusts or anything like that on the bathroom scale, no, because he would be accelerating up and down, but he's standing still. Right? And people tend to do that on bathroom scales. This is number 10. A rock is thrown straight up in the air. Here's my rock, thrown straight up in the air. Here's my initial velocity. At the highest point of the rock's path, which will say this one, and at the highest point, of course, V equals 0 up here. I'll call this V 0, and I'll call this 1, because I don't know what's going to happen later in the problem. Something exciting, I'm sure, because the Regents always has really interesting things. They start with interesting things like rocks, and then they do interesting things like throw them straight up in the air. At the highest point of the rock's path, the magnitude of the net force acting on the rock is... Well, this sucker's in free fall. So the whole time, as soon as it leaves my hand, the only thing acting on it is the force of gravity. Only thing acting on it is the force of gravity. Nothing's changing. What are they getting at here? The magnitude of the net force acting on the rock is less than the magnitude of the rock's weight. Well, the net force is equal to the rock's weight. That's the weight is the net force. Greater than the magnitude of the rock's weight, the same as the magnitude of the rock's weight, 0. The answer is 3. Okay? The net force, which is the sum of all the force, is the object's weight. All right. The direction of the net force is also, I don't know why they had to have magnitude there, but anyway, the answer was 3. 11. This is similar to our explosion lab. Compared to the magnitude of the force, spring A, the spring exerts on cart A, the magnitude of the force the spring exerts on cart B is what? All right. This is, of course, Newton's third law. Which one's pushing harder? A or B? What do we have? A, B. We have a force on B. And we have a force on A. That's a force of spring on B, force of, all right? They're kind of pushing on each other. Remember, if I push on the wall pushes back. Bug hits the windshield hits the bug. They hit equally, even though like with the bug situation, it really seems like there's more force on the bug. It's just the bug can't take as much force without just exploding. So Newton's third law says forces always come in pairs. if I push on you, you push on me, right? So anyway, Newton's third law, these forces are equal. They are the same. Well, what else is the same? Take a moment to think about that. That's right. The magnitude of the momenta will be the same between each one of these. This one will have a momentum this way, and this will have a momentum that way. They will have the same magnitude, but they won't be the same momenta because they will be opposite directions. The velocities will be different, of course. This one will move, since it's more massive, will move with less velocity, less magnitude of velocity or speed, and this one will have greater speed. So the magnitude of the force of the spring is, they're the same. So I guess the choice was 1. 1. An 8 Newton block is accelerating down a frictionless ramp inclined at 15 degrees to the horizontal as shown below. What is the magnitude of the net force causing the block's acceleration? Well, which way is the block going? We don't know. We think we know. We think it's going down. That's what people think, but we don't know that. It's accelerating down, but it could be going up and slowing down. So all we know is it's accelerating down. So there's net force down because really inclined plane problems, certainly the bane of our existence for some of us. Let's circle this. We have a normal force up. There is no friction. So let's draw a free body diagram. I'm going to tilt my axes because I always want to make sure if there's going to be an acceleration, it's only along one axis. So let's make that along we'll call that X and Y. Let's see, we have the force of gravity down here. And this is our angle. How many degrees? 15 degrees. 15-degree angle. All right, our inclined plane problem. So we can break this vector into its components. We have a component down the ramp. We also have a component into the ramp. So I'll call this FG in the y direction equals, in general, FG cosine of the angle. This is going to be FG in the x direction equals the weight times the sine of the angle. FG. There. What's causing the acceleration? Well, this is causing the acceleration right there. That's the unbalanced force because, I didn't draw my normal. The normal force must equal this component of the force of gravity. Getting awfully close to the edge of the frame. These two must be equal. It's not accelerated. That's why I chose this as our axis, because I know it's not accelerating this way. Okay? Any acceleration has to be this way. There's only one force in the x direction, and that is this. So it is Fg in the x direction is the accelerating force, and it's the weight, which is 8 newtons times the sine of 15 degrees. I guess the answer is 2. They didn't want the direction, they want the magnitude. Magnitude just means the amount. But when I see vectors, I want to give direction if I can. Choice 2. 2 is that one. 14. This is going to take a long time. It's going to take a long time to do this. Could be outside. It's Father's Day. I could be outside enjoying it. I'm in the basement. At a certain location, we can't tell you where, a gravitational force with a magnitude of 350 newtons acts on a 70-kilogram astronaut. Perhaps he's not on Earth. What is the magnitude of the gravitational field strength at that location? All right, certain location. I'll say Stromboli. The gravitational force is like an astronaut. Here he is. Here he is. In Stromboli. So gravity is acting on 350 newtons. Fg is 350 newtons. And the mass of the astronaut is 70 kilograms. 70 kilograms. He's got 70 kilograms of stuff. Even if he was in East Amherst, he would have 70 kilograms of stuff. He would have more than 350 newtons of weight. He'd be pulled down more. But he's not. He's in, what did I say, Strambolia? More likely Zambaldagan. What is the magnitude of the gravitational field strength? What is G? What is the gravitational field strength? Whatever. The gravitational field strength is an object's weight divided by its mass. We can find that in the reference table. Let's see, his weight is 350 newtons. And his mass is 70 kilograms. 5 newtons per kilogram, or meters per second squared would also work. I guess we'll go with newtons per kilogram. 2. Of course, that would be a meters per second squared, too. Of course, if we took our astronaut and picked him up and dropped him, we would never do that. We would never want to do that to an astronaut. But if we did, if we took an astronaut, picked him up at this location, dropped him, that would, of course, be the acceleration due to gravity. That is the gravitational field strength, but it's also the acceleration due to gravity if you're in free fall at this location. A spring gains 2.34 joules of elastic potential energy as it is compressed 0.250 meters from its equilibrium position. What is the spring constant of the spring? All right. Well, okay, we got a spring. I'm going to put it on a wall. Oh, put it on a wall. Why not? There we go. We got a spring. Here's our before picture, and here's our after picture. All right, let's give ourselves a point of reference. There it was before, completely relaxed, just enjoying Father's Day, not stuck in a basement somewhere, outside enjoying the sun. Before, and spring gains 2.34 joules of elastic potential energy as it's compressed. It's going to be compressed. All right, there it is. It's compressed. All right, so something compressed it. Perhaps a Frisbee. There's some force. The force of a Frisbee because he's outside enjoying the day, Father's Day. Not in the basement. Spring's not in the basement. So something compressed it, this distance, and we usually call this distance x, or delta x. Regents calls it x, just delta x really, it's a change in position. X is going to be 0.25 meters. That's a quarter of a meter. When you do this, it gains energy, right? You wouldn't want to push that in and then put your eye right there because it has energy and then go think and it would shoot out and transfer energy to your eye, and then you have to go see a doctor. So you don't want to do that. So it has some potential energy because it's because actually the Frisbee did work to it, right? It applied a force and there was a displacement. So there was work being done. That work got stored as elastic potential energy. In fact, 2.34 joules of it. All right. 2.34 joules of elastic potential energy. What is the spring constant? K. K equals question mark. All right. Well, let's just review a little bit. If we have a force versus displacement graph in general, or in this case with a spring, this could be a stretch or elongation. As we compress it, Hooke's law says that if it's an ideal spring, these would be directly proportional to each other. So as we compress it, the force increases linearly, and that's why springs are good for making scales. If we want to know the energy stored, like if it got compressed this much, anytime we have a force versus displacement graph, as long as they're in the same direction, the area under the curve, also known as the integral, for you fancy pants math people, the area under the curve is the energy stored. Energy stored is the area under the curve. That's true in general, not just of the spring, but any force versus displacement graph, right? Force, and we'll say this is displacement. It doesn't matter the shape of it. The area under the curve is the work done. But we don't get into that so much in this class, but we talked about that. Potential energy in a spring is 1/2 kx squared. Oh, this is so easy. Let's just solve for k. This is one of those really easy ones, right? 2 times the potential energy divided by x squared, just solving for that. That looks like it's choice 4. That was an easy problem. Anyways, one way we could look at this if we're just analyzing these problems in general, the potential energy is that, but it's also the area under the curve. This is a triangle, so it's 1/2 base times height, so 1/2 fx, right? 1/2 fx. And of course, we know from Hooke's law that F equals kx, and just plugging that in for F, if we just replace that in there, we would get 1/2 kxx, which is 1/2 kx squared. It's where that came from. All right. 15. When a teacher shines light on a photocell attached to a fan, so we have some sort of photocell, kind of like how you have in your some of your calculators. So you got a photocell, and that's attached. So there must be 2 wires coming out of there, and attached to some sort of motor. And there's a fan, and it's gonna go round and round and round. So he takes, here's a photocell. Photocell. Got a flashlight, shining light on the photocell, causes the fan to turn. The brighter the light shown on the photocell, the faster the blades turn. Go figure. Which energy conversion is illustrated? Okay, so we start off with light, and light gets converted into electricity, and that gets converted into kinetic energy. So what do we have? We have light to electrical to mechanical, right? All right, that's 3. Don't know what to say on that one, really. I don't know. A better teacher would explain it more thoroughly, but it's Father's Day, and I'm in the basement, so I don't care. Which statement describes a characteristic common to all electromagnetic waves and mechanical waves? All right, well, properties of waves. Well, the first thing, well, remember when I tortured somebody in your class by, they were throwing a ball at a cup or something like that, and I made them knock the cup over, and if they didn't hit it, they had to go get the thing themselves. Well, I was trying to show that waves transfer energy, but no matter. Okay, they transfer energy without transferring matter. And then, because when I did it with a wave, I wasn't actually transferring anything to the cup other than energy. The coils that were in my hand stayed in my hand, and if I missed, I didn't have to go get it. So that's one thing. All waves have that. Both waves travel at the same speed. Well, they don't. Both types of waves require material medium. No, actually, electromagnetic waves would rather not have a medium. Well, I don't know, they don't really decide, but they travel the fastest without one. So I would think they're happiest when they don't have a medium. Both types of waves propagate in a vacuum. Well, sound doesn't. Or a mechanical wave needs a medium. Both types of waves transfer energy. Yeah, that's what they do. They transfer energy. So 4. One other thing on this one. The thing that determines the speed of a wave, of course, is the medium. And that's the only thing that really determines the speed of a wave. The frequency or any of that stuff doesn't affect the wave. So that's an important thing to remember. 17. An electromagnetic wave is produced by charged particles vibrating at a rate of 3.9 times 10 to the 8 vibrations per second, also known as a cycle per second. They just gave us a frequency. Frequency equals 3.9 times 10 to the 8th vibrations per second. I wonder if those are good vibrations. 3.9 times 10 to the 8th cycles per second would be another name for that vibration. That's second right there. Vibration. So I could use a better wave term there, cycles. Okay, so these oscillations are going to cause an electromagnetic wave. All electromagnetic waves are due to accelerating charged particles. So let's see. What wave has 3.9 times 10 to the 8th cycles per second? It's looking like radio waves. That's one radio wave, I guess. The energy of a sound wave is most closely related to the wave's frequency. Nope, that's the pitch. Wavelength, no, not the wavelength. Not the speed, it's the amplitude. The amplitude of a sound wave is the loudness. I don't know. I don't have anything else to say on that one. You know? 19. A sound wave traveling eastward through air causes the... Okay, it's going eastward. East. Let's make it that way. Eastward. A sound wave. So it's a sound wave, so this is of course, it's going in 3 dimensions, but I can't really draw it that way. It's getting wider and closer together, and then wider and closer together, and then wider. These aren't any shorter. But anyways, so they're kind of going like this as they go. It's going this way. It's got a velocity this way. Velocity's that way. And these guys, these are like little molecules. I could have drawn as molecules. I don't have time to draw molecules, so I drew them as lines. So it's vibrating back and forth. Each one of these is actually vibrating back and forth like that. Each one of these is going back and forth like that, going like that, just going like that. Not really moving anywhere, you know, just kind of vibrating back and forth this way as the sound goes that way. The vibration is east and west. If it's going that way, these guys are vibrating east and west. What else do they say? North and south? Certainly not. North and south, if this was certainly, no, I'm not even going to draw that because it's too hard. If that's east, then north is that way. If this was a light wave, it could be going like that, but I can't even draw that on the board because it's in a different plane. What is the speed of light in ethyl alcohol? Speed of light in ethyl alcohol. All right. So remember, we have the speed of light in a vacuum. All forms of electromagnetic radiation travel at this speed in a vacuum. That's a constant. And very important, given a special letter C. That's, of course, remember that from the equation. E equals mc squared. Right? Remember that? I remember that. It's going to go slower in another medium, in this case, ethyl alcohol. The index of refraction gives us an indication of how fast that is. Ethyl alcohol, 1.36 is the index of refraction in ethyl alcohol. Oh, and they gave us the frequency. Why did they give us that? So that we could use our reference table for ethyl alcohol, because it's only the index of refraction. Of course, that tells us that the index of refraction is a function of frequency. At a different frequency, different color or type of electromagnetic radiation, that would be different. What is the speed in ethyl alcohol? What's the speed of ethyl? Ethyl. There's no business like show business. All right. Ethel Merman reference. Nobody gets it, I know. Anyways, index of refraction is defined as the speed of light in a vacuum divided by the speed of light in that material. In this case, speed of light in ethyl equals C over N. And remember, it slows down, but they never slow down that much. It's always going to be times 10 to the 8th meters per second. 2.21. How fortuitous! 21. In the diagram below, an ideal pendulum is released, A swings to B. As the pendulum goes to B, what happens to its total mechanical energy? What makes an ideal pendulum ideal isn't the color or the prettiness of the bob or the shininess of the bob, even if you don't find shiny pretty. It's that there are no losses. There's no internal energy, no energy transferred to internal energy. So it swings forever. There's no wind resistance. or anything like that. So a real pendulum is close to that. So its total mechanical energy remains the same, 4, okay? As it swings, here's its highest point, and it's going to go over back to the same height, and here's the lowest point. Remember energy pi, that's the highest point, so it's going to be at rest here. All the energy will be potential energy. Here is its lowest point. We'll say it's all kinetic energy. We're going to say potential energy is 0 at this level. Remember, potential energy is a relative thing, so we get to define what we call 0, and it's convenient usually to call the lowest point in a problem 0. Not always, but a lot of times it is. I'll say 0, all kinetic. Energy pi is the same size in all of these, even though my limited artistic abilities might not make it look that way. And then if it was halfway, then it would be half potential and half kinetic, or whatever, be distributed somehow. 22, the diagram represents a periodic wave. What kind of wave is that? Take a moment to think about that. Of course, that's transverse. Which 2 points in the wave are out of phase? Points in the wave are out of phase when they're doing, they're in phase when they're doing the same thing, and they're out of phase when they're doing different things. Let's say the wave's going this way, just for the sake of argument. So A, for instance, is at the equilibrium position. In fact, all these are at the equilibrium position. Which way is A traveling now? A is actually traveling downward at this point. B is traveling upward. Understand that if you don't, you need to make sense of that. I'm not going to spend any time doing that. C is going downward, A is going upward, and so forth. Which 2 points are out of phase? A and C are doing the same thing. They're in the same position relative to the equilibrium, and they're both going down. They're the same. A and C are in phase. B and F are in phase. They're both, F is down here someplace. They're both going upward, the same position. C and E are both going downward. And D and G, D is going up and G is going down. D and G is the answer, 4. D and G are not in phase. In fact, they're 180 degrees out of phase. 23. A dry plastic rod is rubbed with wool cloth and then held near a thin stream of water from the faucet. The path of the stream of the water is changed as represented in the diagram. Which force causes the path to go? All right, so when we rubbed this rod, it became charged. I don't know how it became. I don't know if it's positive or negative. I could look it up, but I'm not going to bother. Let's just assume that it got, because it doesn't really change the problem. Let's say it became negatively charged. I don't know. I would have to look up the triboelectric series. How did it become negatively charged? Well, it must have acquired the same, negative charge from the cloth. When they rubbed together, the cloth gave up some electrons and had some protons. All right, so it's near water. Got these water molecules. Water molecules are already polarized. They're polar molecules anyways. But anyways, so we had these water molecules, and they have a negative side and a positive side. So they're going to arrange themselves like that. The negative is going to be repelled, the positive attracted. So it's going to experience a force this way. Of course, a rod experiences the same force, Newton's third law. So there's an electrical attraction like that. And if you remember in class, I did this with a comb. And you can try this at home. It's great fun. You already missed Father's Day because today's Father's Day, so you haven't seen this yet. But next year, Father's Day, you should take a comb, run it through your hair, and say, Dad, hey, check this out. Run some water down. Say, look at the water's coming over. Ha ha. Yeah. Your kid learned something in school. Which force caused the path of the stream to change? Let's see. That is electrical. That's electrical. Not nuclear. Nuclear forces only exist within the nucleus. And this, of course, is outside the nucleus. The force is occurring over space, over a large distance, actually, compared to a nucleus or an atom. So this is an electrical force. And the only forces that exist outside the nucleus would be gravity or the electromagnetic force. But this is electrical, not magnetic. So this was 3. All right, let's draw a picture. So we have some sort of water wave. There we go, water wave. And it looks like we have a centimeter between successive crests. Every 0.4 seconds. All right, so it takes, so every 0.4 seconds, that sounds like a period. Period is 4.0 times 10 to the minus 1 second. All right, so it takes, so every crest, like here's a point right there, pointy. There's a point, and it's going by every 4 times 10 to the minus 1 second, goes past that point. That's a period. This, of course, is a wavelength. Wavelength, 1 point, is a centimeter. What is the speed of the wave? How fast is it going? Speed in general equals distance divided by time. Well, the distance from there to there is the wavelength, and the time it takes to go to repeat that motion is a period. That looks like choice 3. 3. All right. Number 25, a vibrating 256 hertz tuning fork transfers energy to another tuning fork, causing the second one to vibrate. This phenomenon is an example of, well, I did this in class, remember? Remember that? And it didn't vibrate much, but if I put another tuning fork next to it, remember? I had one tuning fork going back and forth at 256, and that made another one vibrate just by being near it. It was in a box. Remember, they were in a box. And then when I went, that was me, and I went, nothing. Nothing. Even though I put more energy in than the other tuning fork, it didn't cause it to vibrate because it wasn't the right frequency. You have to put energy in at the right frequency. If we do vibrate something at its natural frequency, a small resonance, a small amount of energy can cause something to vibrate. The other example we saw was with the snare drum. When I put different frequencies to the speaker, it went whee, I would take the little thing that made the different frequencies, and at certain frequencies you'd hear the snares underneath the drum vibrating. Anyways, but and remember that guy, the guy. Did you try that at prom? Did you try that at prom, yelling into the glass water, see if it could break? I don't know. The answer is 4, resonance. That's resonance, 4. Sound waves are produced by the horn of a truck that is approaching a stationary observer. This is sounding like it's going to be the Doppler effect. Compared to the sound wave detected by the driver of the truck, the sound wave detected by the observer, all right, here we go, got observer. There's our observer. Very observant, big eyes, big ears. Big ears on our observer. All right. Motorcycle coming towards us, right? Right? Okay, and that is because, I'm going to try it one more time without drawing the truck. The waves are bunching up on this side, giving us a higher frequency, shorter wavelength, and they are wider behind. So the person over here would hear a lower pitch. Here they hear a higher pitch. Has a greater frequency, higher frequency. So frequency. And this is called the Doppler effect. I guess that's a capital. It's called the Doppler effect. It's the only time we see a change in frequency. Frequencies of waves generally stay constant except under conditions of the Doppler effect. So the frequency is higher, 2. The wavelength is actually shorter, less wavelength. So we have electron volt as a unit, and we have two things in it, electron and volt. Electron is charge, and volt is voltage. All right. This is a measurement of, well, let's see something that relates voltage and charge. If we look up in our reference table, we'll see voltage equals energy divided by charge. We use W for energy in this case because we don't want to use capital E because that's used for electric field with electricity. So energy equals voltage times charge. This is energy. Energy. Electron volt is a measurement of energy. Choice 1. Which particle could produce a magnetic field? You need moving charges to produce a magnetic field. End of story. Magnetic fields are caused by moving charges. Charges moving relative to each other, actually. So the answer is 4. Magnetic fields are produced by moving charges. We see it generally in two ways. One, we could have charges in a wire, right? So basically we have current. That will produce a magnetic field. In fact, the magnetic field, we could figure out the right-hand rule. Remember, it would we would get these magnetic fields that circle around the wire. Or in a permanent magnet, north and south, we had electron spin, which is causing it. And with magnetism, remember, always forms closed loops. And to determine the direction of the magnetic field, and of course it's on both sides, they never cross. Like that, where they're closer together, the field is stronger. Where they're farther apart, it's less. And the direction is determined by the direction a compass would point. So if I put a compass here, the north, it's going to be in this direction because the north side is going to be attracted to south, and south is going to be attracted to north. A physics student takes her pulse and determines that her heart beats periodically 60 times in 60 seconds. What is the period of her heartbeat? Well, period is a measurement of time, capital T. So we must have seconds in the numerator, times in the denominator is 1 second is the period. 3. Moving 4 coulombs of charge through a circuit requires 48 joules of energy. What is the potential difference across the circuit? All right, so we have some sort of circuit. And we're going to move charge through that. 4 coulombs. So I'm going to use W for energy. This is one of those unfortunate just kind of plug and chug problems. We want to know what the voltage is. What is the potential difference from there to there? That is going to be voltage is the amount of energy divided by the amount of charge. Know your units in electricity. Know your charge has units of coulombs or elementary charges. Coulomb is the standard unit. Know that we can only have whole number of charges, so our elementary charges always have to be whole numbers. 31. It's just like cars going into intersection. The number of cars coming in have to equal the number of cars leaving. So I'm going to make a chart to make sure I don't mess up, especially if we had a lot of them. This one's kind of easy. But anyways, let's start here, I guess. We have 5 amps in to the junction. It's going in to the junction, 5 amps. 7 amps in to the junction. 3 amps going away from the junction, 3 amps. Add these up. That's 12 amps. And what do I need to add to that to give 12? 9 amps. I need 9 amps to balance that out. All right, 12 amps. And they would be balanced. The amount of charge in equals the amount of charge out. So we had 9 amps out, but they don't ask about it. The choice is 3. 3. Electric dryer consumes, let's see, how much energy? 6.0 times 10 to the 6 joules of electrical energy. Use W for electrical energy. When operated at a voltage of 220 volts for a time of 1.8 times 10 to the 3 seconds. How much current was that drawing? All right. So we have an energy relationship that looks like this. Energy equals VIT. Therefore, the current equals energy divided by voltage times time. 15.2 amps. All right, what is that? That is, we only had 2 significant figures on this one, though. So that would be choice 2, 15 amps. Which net charge could be found on an object? All right, so they give us in coulombs. We need to convert this to elementary charges and make sure it's a whole number. Let's see, an elementary charge, we looked that up in our reference table, is 1.6 times 10 to the minus 16 coulombs. So, and of course, that is also 1e. So it has to be a multiple of that in coulombs. Looks like that first one's going to do it for us. Let's see. So what you want to do is 4.80 times 10 to the minus 19 coulombs. Let's convert that to elementary charges. Multiplying by 1s. These are equal to each other, so let's make the coulombs go away. So I'm going to put coulombs in the denominator, elementary charges in the numerator, and I think I end up with 3 by doing that. So the first one was the answer. If we took a look at, let's just take a look at number 2 for the sake of it, 2.40 times 10 to the minus 19 coulombs. And then if we multiplied this by 1s, I think we would quickly see that we would get some sort of irregular number. 2.4, not irregular, but not a whole number. So we end up with 1.5, and you can't have that. Can't have a fractional charge, except in a quark, but quarks always exist with other quarks. We're almost done with the multiple choice. We always want to do real well on multiple choice. A photon is emitted when the electron in a hydrogen atom goes from n equals 5 to n equals 3, directly to n equals 3. What is the energy of the emitted photon? All right. So we had these orbitals, 3 to 5. 1, 2, 3, 4, 5. Okay. So is it 5? And drops down to 3. Zoink. Goes down to 3. When it does, it gives off a photon, and they want to know the energy of the photon. So I'm going to need to look up some numbers. The energy at 5 minus 0.54 electron volts. Energy at 3 is 1.51 electron volts. What is the energy of the, okay, it's even in electron volts, so that's easy. Energy of the photon is going to equal energy initial minus energy final equals minus 0.54 electron volts minus a negative 1.51 electron volts. Electron volts. So that is going to be choice 2. In the process called pair production, an energetic gamma ray is converted into an electron and a positron. It is not possible for a gamma ray to be converted into 2 electrons because there's our photon, and it's energetic. It's gamma. And it is going to be, it's going to be converted into an electron and a positron. So a positron is just the antiparticle for an electron. It would actually look like this. Symbol would be like that. And we'd put the anti-symbol on top. So it has opposite charge. Every other characteristic is the same mass and everything. Now, we know that this can't turn into 2 electrons because there are certain things in this universe that are conserved, and one of them is energy. That's a quantity that's conserved. As far as we know, the amount of energy that exists today always existed. Momentum. Momentum in a closed, isolated system is conserved, and also charge is a conserved quantity. And since our gamma photon started off neutral, the things that it turns into must collectively be neutral. In this case, since this is an electron, this has to be positive because this has a charge of minus 1e, and this has a charge of plus 1e. So it's neutral. So charge must be conserved. Momentum is also conserved, but that wouldn't explain why you can't have 2 electrons. All right. So that is it for the multiple choice.
Extreme physics.